As a bonus video for this parametric wall video series, or at least this portion of the video series, I wanted to give you additional options for constructing panels on surfaces inside of Grasshopper. So we looked at box morphing and applying box morphs to surface boxes as one way of operating on surfaces developing panel geometries. That's more focused, though, on volumetric operations being applied via the surface box to the surface divisions. So instead of looking specifically at constructed surfaces and the divisions of them, I want to look in a little bit more of a focused way at the curved divisions that we made at the beginning of that last video, and take a look at how those divisions can be distorted to make a parametric fin system for a wall construction. So the output of this video should look something like this, where we have controlled, constrained geometry. So if I zoom selected here, we can see thickened fins, which actually have a parametric control over the gap between fins, smooths into one another, and these are all singly curved fins that can be unrolled and cut out of sheet material and then bent into the geometry you're seeing here. Everything in this is parametrically controlled, which means we could easily fit this into any project that we were currently working on. So in order to get started with this, what I want to do is take a portion of the output from our last video, so one of the steps, and that step is going to be the point that we drew out the midpoints from our two curved divisions. So just a reminder, I'm going to copy these and make a new file, and we can go ahead and get started from there. So if I go to File, New Document, and then I'm going to just paste these components that we already have, and I'm going to go ahead and hide that output from our view in our Rhino file. Okay, so with these curves in view, I'm going to just take us through the components that I'm using here to give you a better idea of which step we can use or start from for this bonus content video. So I have both initial points of the curves, so all of those components are still showing. So if I preview these, we can see that that's the original point set drawn out in space, which we then have built curves from. So we draw curves through that set of points using the graph mapper to parametrically control them. And if I hide this curve, or these curves, we then have divisions drawn across those curves into equidistant segments, and we're taking those points, we're drawing lines between them, we're then constructing a midpoint between those lines, we're then deconstructing that midpoint and using a graph mapper to rebuild that midpoint into an adjusted version of itself. So we now have this other new set of points there, and what we did in the last video is we also drew a third curve through these sets of points, just like we did with these NURBS curves before it. We're going to do something a little bit different in this video, which in order to get started, we're actually going to take a look a little bit deeper at these divisions here. So I'm going to hide the preview on everything else, and we're just going to take a look at one of these division sets. So we have 3 of these point sets that we can use to construct a curve because they're a flattened list of points. Now, if instead of drawing a continuous curve through here, we just wanted to go from the first point and just draw one line, just one, from the first point just to the second. The way to do this would be to use a list item component, and we're going to take the entire list of points plugged into our list. We're going to give it an index, which is going to be 0, so our 0th index is the first point in this list. We can see that visualized there, so that's the left point. And if we wanted to draw a line from here to the second point, we would just copy this, and instead of 0 index, we would give it an index of 1. We can see that that's now showing the second point. And then we would make a line component connecting these 2 points, and we now see that connection drawn out inside of Rhino. So having to copy this and do it the kind of brute force way by copying every single one of these and then going from index 1 to index 2 would be incredibly brutal. It would be an incredibly brutal way of doing this. Fortunately for us, we can just manage the data structures inside of Grasshopper to kind of automate this for us. And this is really the beauty of programming. So instead of calling out each individual item, what we can do is say, for each item in this list, so for every single point, I want to draw a line between this current point and the next one. So what this looks like is we have to first make a line component again. We can draw a connection between these points, and those are going to be all of the first points in this line. And then we want to connect each of those points to the next point. So Grasshopper actually has a component called shift list, which is going to take that list and just shift it up 1, meaning that the first item in that list will become the second item in the original list. So everything just shifts. So to use this, we just have to plug in our list. So we can plug in that list of points. We can see that the first value here is 0, 0, 0, and then the second one is 1.32, 0.19, 0.15. If we look at the output, we now see that that second point becomes our first, and everything else shuffles up. We can also see that the last item is actually that first point, 0, 0, 0. If we don't want to draw a line from the last point all the way to the beginning, which we don't in this case, then we need to set the Boolean toggle for wrap to false. I can show you what that looks like if we don't set that to false. So if we plug in this list into B, we actually get all of those lines drawn out, and then it gets all the way to the end and goes back to the start. So we don't want it to go back to the start, so instead we want to say wrap equals false. Now we have a number of lines drawn out connecting each of these points. If we copy these components, we can also do this for the top set. So now we have several lines drawn out connecting that top curve. This is pretty similar to what the NURBS curve is doing by connecting all of them, but we're just separating them out into each individual segments. This way we have more control over the panelization. If we copy this again, we can do this for our middle points as well. So I'm going to take these middle points, plug them into A, plug the points list into our shift list, and now we have a series of lines drawn out in the middle section as well. So if all we wanted to do was panelize this, we could take a Loft component, we could merge all 3 of these. So take our lines, plug it into D1, and then the middle into D2, and then our top into D3. So we have 3 sets of lines and plug them all into our Loft component. And before we do this, I think we're having that issue with some of our data management. So these midpoint lines actually have an extra branch in them. So there's a couple of ways that we can deal with this, but one of those ways is going to be to graft or separate each of the branches for these lines. So we'll basically just be looking at just the first line with just the first line in the next one and just the first line in the third one. So in order to do this, we need to right-click on the output and select graft. And then we need to right-click on each of the other outputs and select graft for them as well. And now you can see that each of these panels is drawing from the first line in the first curve, or first set of points, to the first line in the second set of points, and the first line in the third set of points. So we have these kind of complex sweeping lofts, and that's because our loft option is not straight sections, but instead the loft options is the normal, which is what it's called, which projects a smooth surface through all three of those line sets. So we could just do this, and we could go ahead and bake that. And that will give us these kind of surface fins drawn out across our surface. But if we want a little bit more control, especially because these look a little bit kind of blobby and loose in the midsections, and also they start to lose some kind of rigor in constraining to only singly curved geometries, which are things that we need to focus on when we think about fabrication. The way that we'll start to constrain this is not by just lofting all the way through, but we'll loft in individual sections. So instead of merging all of them together, we can just merge two separate sets. So first from the bottom to the middle, and then we'll do the same thing from the middle to the top. So now we have two separate sections there, and if we wanted to, we could just join those and bake them as well. Why don't we just go ahead and do that just while we're thinking about it? And we'll go ahead and flatten these as well so that it joins as one continuous poly surface. So that's much cleaner. We have a crisp edge in that midsection there. So much nicer than that first set of lofts that we had. Keeps the cleanliness of the geometry, and we only have twisted surfaces, but singly curved ones based on ruled surfaces, which is really nice for fabrication. So we can go ahead and leave this over here just to remind us where we started. But what if we want to actually open up some of these panels to allow light in so that they're not all opaque? Maybe we have a glass surface behind these, so we want just a few of these to be pulled up, or corners of them to be pulled up, so that we can allow light to enter in. Well, the way that we're going to do this is by editing these midpoints and taking one set of these midpoints before we draw the line and actually moving those and then drawing this line. So I'm going to go ahead and move these final set of surfaces, go to where we have this line drawn out, and the one that we actually want to move is just this shifted list of points. So if we wanted to move this, we would start by making a move component, plugging in those points, and then plugging in the output into B. Now by default, this gives us a vertical vector 10 units tall. So this definitely doesn't work. It looks a lot way too extreme. So instead, what we might want to start with is a unit vector just in the y-axis. So just adding depth to the wall surface. And this is because we know that it's arrayed along the x. So I'm going to say unit y, and this is going to make a vector that is exactly 0, 1, 0. So if I plug that into our translation vector, now every single one of those second points in this list have moved out exactly 1 unit from the original. So you can see these are the original and these are the moved points. And then those lines now are drawn from the first point in, and it continues to be drawn in. If we want to control, instead of just using a fixed value, but we want to actually control that amount of movement, then we could just input a number slider here. So we could say negative 4.0 is less than 4.0, enter, plug that into our unit vector, and now we have full control over how much those fins are moving. So we can control, let's say, the amount of light passing through or coming into whatever is behind this wall surface. Another way of doing this is actually, like we did here, to take whatever the values are of these points and then use some specific data property about them to affect the amount of movement that we have. One common way that we can do that is actually with something called an attractor point. And what an attractor point really just is a measurement of distance to some given point. So I have a point already drawn in Rhino here, but we can just go ahead and make a point in Rhino by typing point in our command line, and then we can move this wherever we would like. And then we want to reference that point inside Grasshopper. So I'm going to double click in Grasshopper, type point, right click, set one point, and now we have that point set inside of Grasshopper. So we want to take every single point that we're moving, so all of these points, and we want to move them by not just a fixed 0.4 value, but some amount relative to the distance from these points to our point in Rhino. We can do this by double clicking, typing distance, and this gives us the measurement of distance from a given point A, so that's going to be our Rhino point, to a desired point B, which is going to be all of these points along our middle section there. And now if we make a panel, we can get the values for all of these distances. Now, as we move this point away, we'll see all of these values increasing. But we could be moving this point 100 units away, we could move it 1,000, 10,000, 100,000, and we really have no idea what the actual bounds for this distance value is. So when you're using an attractor point, one of the first things that you can do to clean up this process is to actually redistribute or normalize this data from a range of 0 to 1. So you can think of this as basically finding the maximum, which is 24.42 here, and then finding the minimum, which looks to be 6.90, and we want to take that domain of 6.9 and 24, and we want to remap that from 0 to 1. We can do this with a component in Grasshopper called remap. So this is remap numbers, and it basically remaps a set of numbers based on an initial domain and a target domain. So the target domain by default is already 0 to 1, which is actually what we're going to keep. We want it to be 0 to 1. But our source domain, which right now is 0 to 1, we want to be 24 and 6, so 6.9 to 24. We can get that as a domain by typing bounds, and this gives us the minimum and maximum of a list. So we can take this distance list, plug it into our bounds, and that gives us that domain of 6.9 to 24.4. So we'll plug this into our source, and then we'll plug the distances in to our value. So that means it will take in every single one of these values, and if we put a panel on the output, we can see that each one of those, so the maximum 24, gets remapped to whatever its corresponding value is in the new domain. So 24, the maximum, is now the maximum of the new domain, which is 1, and 6 was the old maximum, but now it's 0, or minimum rather, so now it's 0. So we've remapped those, and now they're primed and ready for us to be able to use a graph mapper, which defaults to a domain of 0 to 1. So we can plug these in as an input, and then we're going to use this graph mapper to override this set of point translations. So instead of 0.4, we're going to use the output from the graph mapper, and I'm going to just move these components along so that we can see that they're after this graph mapper. And now we just need to set the type of graph we want to use. So we can right click, go to graph types, and this time I'm going to use Bezier because it gives us more control over the kind of kinking or degrees or movement with which we might want to apply to this translation vector. So right now it's linear, so it's going to stay the same. But if I drag these points down, we should be able to see that affecting our geometry. So the point closest to our attractor point is going to be 0 in the X. So it's going to be the farthest left on this graph mapper, which we can see right now is a Y value of 0, so the output value is 0. That's why the closest point here, or the closest panel, has the least amount of flap, or the least amount of opening. Now as we drag this point up, it now becomes the most open. And if we want a kind of tighter transition there, then we can just drag this control point or handle over, and now a majority of the surface is closed and it opens just at the end there. If we wanted to exaggerate this more, we could double click on our graph mapper, and then we could expand from, instead of just 0 to 1, we could make the Y domain 0 to 2, hit OK, and now we have a more exaggerated domain there, so we can make a larger flap. And we can control how this transition happens, so we can make it slightly slower to transition, or we can drag this handle all the way in to make it a quicker transition there. So maybe I'll go somewhere in between to start, and we'll do something like that. Okay, and now once you've done that, we've applied the actual openings. The next step is just, instead of to just immediately join these, we want to join them and then perform some smoothing operation. And just like in the first Rhino video, what we want to do is we actually want to apply a fillet edge. And that's going to be this kind of volumetric looking one, so fillet edge, which will apply to surfaces or B-reps. We're going to take the output of this join set of B-reps, should be able to, actually, I think in this case we want to unflatten this list. And the reason we want to unflatten this list is because we just want each of the corresponding panels, so each of the panels in the specific branch of each, the kind of top set and then the bottom set, to join together, but we don't want all of the list to join together. So when we want all of the list to join together, we tend to flatten. If we don't want all of the list to join together, we tend to either leave unflattened or we tend to graft, meaning that each branch is going to be its own kind of object and iterated through individually. And this is really great for coordinating multiple lists where we need to iterate through individual panels or individual elements or items. Okay, so now we just need to go through the inputs for this fillet edge and see what it takes and how we can infill those. So metric rolling ball is totally fine. So these are just ways that it's actually going to perform that fillet operation. Then we have edges. So if we're thinking about the edges, and we know that these panels are basically just two panels joined together, and we have three edges defining them, our three lines that we made, so the bottom, middle, and top. Our bottom line is going to be index 0, our middle line is going to be index 1, and our top line is going to be index 2. Because our indices always start from 0 and then go up from there, we know we have 3, so 0, 1, and 2. We always want it to be our middle index that is the one that has the radius applied. That means we want our edges, or the index for our edges, to be 1. So I'm going to make a 1 slider here and input that into our edge indices right here. And now we have an error that says at least a single radius is required. And that's just because we haven't input any radius value in our radius input. So if we want to get rid of this error, we just need to make a new slider from 0.1, and then I'm going to say less than 1, and we can plug this into radius. Now we can see a very small radius that's showing up there on our lofted surfaces. And we can hide the preview of everything prior to this so it's a little bit clearer. And as we increase or scroll up the radius, we can see that that larger radius is being applied to the geometry. So we're getting that nice clean radius applied to these fins. Now, we could just leave it at this, and we could bake this set. And then move these over here. Or if we wanted additional control, and not just to fix that radius at a radii of 1, but we actually wanted to control, like we did with the point movement, the amount of radius applied to each one of these panels. What we could do is just take the output here from our graph mapper, and we could plug that directly into radius. Now when we do this, it's going to give us an error. The reason why it gives us an error is because we have more radii than edge indices, right? So we're inputting into the radii 16 values, but we only have one edge input into our edge indices. In order to make these values uniform or matching, we need to match the data that's going into these two inputs. We can do that with something called cross-reference. And cross-reference basically takes an input set. So this time it's going to be the output from our graph mapper. And then it takes another input set, which is going to be our value of 1 for the indices. And what it does is it makes them the same type of data, meaning the same amount of data. And you can see that even the paths are exactly identical. So this is automatically pairing all of our B values, and it's matching them with the A values. So we have 0 to 15 and 0 to 15 in both of these lists, which is fantastic. That's what the error is saying that we need. So now what we want to do is feed in the A value of all of our radii to our radius input, and then all of our B values, which is all of these 1 indices, into the edge indices. Now we have that input into our wall here, and we're just getting one warning, which is saying that edges may only be filleted once. But I think this is not going to affect the outcome. It probably has to do with the distances being applied, or the radius being applied relative to the proximity of these edges, and it might be having an issue with some of those. So if we select this output, we can right click, bake, select last, and move it over here. And it's a barely noticeable difference, but you can see this is a little bit tighter because we were using a radius of 1. And this actually has a control where the radius gets smaller as it gets further away from that attractor point. And since this is a parametric setup, not only can we just have this 1 finished, but we can also now move this point in space, and it will, we're getting a little bit of error where the radius is clipping the end. But as we move this, we can see that it is updating with proximity to our point. So we get these fins opening up as our point moves closer to that midsection. And now we can go ahead and bake that, move it over here, take a look at each of these panels again, and we can see that difference in placement of that opening. So this is really fantastic for things like ventilation, or allowing a kind of controlled degree of light in past some wall surface. But also something important to note is that each of these panel sets perfectly nest into one another. They align on the edge. They flatten and have controlled radii all the way through. So if we select one and type Unroll Surface, we can see these surface panels unrolled. And with them joined, all you have to do is cut the outer profile, and you could score these 2 lines on the inner radii, and that would allow you to bend this strip to form this parametric fin wall condition. So that's all for this bonus video. I just wanted to show this as an alternative to the workflow that we went through using Surface Box Morph.